Okay, so in this first lecture, I will discuss about the Kubo formula and I will connect the Kubo formula with the Green's functions. That has been done in some textbooks, but I will like to give a small or short uh, derivation so that can bridge the gap uh, with your undergrad or grad quantum mechanics to this Kubo formula. Okay, so we start from the well-defined time-dependent Schrodinger equation. So this is the time-dependent Schrodinger equation. So we have the time derivative of the wave function, and this is the Hamiltonian. So this is the first step, and the second step is like you have the Hamiltonian, and this Hamiltonian consists of two parts. So the first part refers to the sample, so H0 refers to the Hamiltonian for the sample, and the second part, that is V of t, this refers to the external potential. So this is important. So the potential, the perturbation can be internal perturbation like electron, 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 phonon. But we are not talking about those perturbation. We are talking about external perturbation. When we are discussing Kubo formula, then we are discussing about the external perturbation, and that is this perturbation V of t. Imagine this is your sample. So you have this sample and you connect it with this voltage, and you are observing current passes through this sample. So this is important that this sample Hamiltonian is defined by this H0, and this external potential V is the perturbation that you have applied on this sample. So that's it. Okay, so here the potential mean, or the perturbing potential mean, the external potential that we are applying to see the response of the system. That's what Kubo formula speaks about when it speaks about the perturbation. That is the external perturbation. Now we try to utilize the machinery of complex algebra, and we utilize the imaginary time formalism because it will make our calculation much easier to deal with. So this is the imaginary time. So what we do, we change it with tau. So this is the imaginary time. So if we do this modification, then our time dependent Schrodinger equation becomes like this. And this looks good. Now here is the point, that when we try to solve the Kubo formula, this is assumed that you know the sample Hamiltonian. So H0 solution is known, so you know its wave function. So like you have the parabolic electron gas P square by 2m star, that represents the gallium arsenide or semiconductor structure. So you know P square by 2m star, or it can be like graphene. So this is your H0, or it can be graphene, that is Vf sigma dot P. So you know H0 and its solution, its wave function. But what we want to know the interaction of this sample, that is gallium arsenide or graphene, when you apply external potential like electric voltage or some time dependent interaction or magnetic field. You want to see the response of your sample. So this is their sample. So this is better to not worry about this H0 part of this time-dependent Schrodinger equation. And in mathematics, we can devise a technique that is used, that is well known in quantum mechanics, and it is called the interaction picture. So what they basically do, they replace this wave function into the known part, so that this reflects the known part, and this reflects the part that only deals with the interaction term. So the benefit of doing this is apparent in this equation, that you can see now the time dependent Schrodinger equation. So this is once I have substituted the wave function for the system in terms of interaction picture, and now you can see I have inserted it here, and now I simplify this. Okay, so this is the advantage of this time-dependent interaction pictures, that we have only external interaction term that is now in time-dependent Schrodinger equation. And here this is the interaction potential So we have h0, so we have like these unitary weights that is multiplied in front and in back of this operator or external potential. So this is a very standard linear equation in time that one can solve. So this is the exact solution of this wave function, or this gives you the time evolution of the wave function. The strategy, and you can here find out to up to order or up to arbitrary order the correction due to the external potential. But that is not the theme of the Kubo formula. The Kubo formula is the linear response tool, so you only need to worry about up to the linear order. So what you can basically replace this time dependent variable tau prime that is integrated upon by just tau 0, and by doing this you are basically taking this first term and putting it in here to find out the first order correction. So this will give you the first order correction. So this is enough for the linear response work. And so we have find out an equation that tell us the response of the system due to an interaction. So what happened is you have the system at time t equals to 0 and the interaction is not present, like the electric field or a magnetic field. At time after time t0 the interaction turns on, and then you calculate its response at later time that starts from tau 0 and go up to tau. Okay, now we have this evolution of the state in time, and now what we want to do, we want to now you can calculate the response of the system. So let's suppose we want to calculate the expectation value of operator A. This operator A can be current, density, or anything. We want to calculate it, and we want to see the external field, how the external field fluctuates it, or how the external field can induce fluctuations. So this is the standard technique or formula to calculate the thermal average for this function. So this is how you find out the expectation value. Here z is the partition function, and one should keep in mind in partition function you only deal with the sample h0, not with external potential. And you should not do this because this is a linear response, and there are other reasons as well that we don't include external potential in the partition function. So you can find out the expectation value of any operator A, and here this is written in interaction picture. This means in front and in back. At back there will be these unitary weights on this operator. So what you do now, you expand this or you put here this function or this solution which is in actual the wave function time evolution here, and then you can find out the zeroth order term, that is the expectation value of operator A at equilibrium, and then the first order correction due to the external potential. So this is the first order correction term, and this is linearly proportional to the external potential. So this is it. So we call this the equilibrium expectation value, and this is the fluctuation from the equilibrium. So so the fluctuation from the equilibrium is the expectation value of the operator A at time tau, and its value calculated when the interaction was not turned on. So this difference will give you fluctuation or first order correction. So this will be in a actual or basically equals to this term. Okay, now we move forward. So now we have this operator or the fluctuation in operator due to the interaction. Z is the partition function. Okay, so this operator is here. This is the commutation relation between this operator A and this interaction potential. That is. So we also should discuss about what this interaction potential is. I will discuss it later on as well. But in actual, the interaction potential will be interacting with the current density or with the charge density or the viscosity. So what it will be in the form of like So like in case of current, it will be like J dot delta A, or so, yeah. So this type of potential this will be. But here we could also okay. So this I just wanted to mention separately that what this interaction potential can be, but and here this is the commutation relation. Now what I want to do is I want to write this in more compact form that I can do by using the time ordering operator technique. So that is I can replace this commutation relation by the time ordering operator T of tau. So time ordering operator automatically cater or take care of the ordering of this operator, and this commutation relation is automatically taken care of. Or one should like try to know about what is time ordering operator, and that is there are standard textbook that discuss it. So basically what happens that the earlier time always so you need to take care of the time ordering, like the earlier time operator will be acting first, and then the later time operator will be acting. So this is how the time ordering operator works. Okay, so this is the fluctuation in the expectation value of the operator A due to the external perturbation. So this is it, and we are trying to write this in terms of the Green's function. So this external potential is basically uh, is written in interaction picture. So I can once again decompose it, and I see that there are unitary weights, that is h exponential of h0 tau prime by h bar and this term. So similarly, I can do this with the external potential, and I ended up with this equation. Now I am trying to write down this equation in terms of the Green's function. So I am doing these type of steps, and and this should be like systematic, and one should understand what are the implication of these steps. So I want to write down because I know this operator and these operators don't commute each other. So I want to first set these operators in a form that I can convert them into Green's function. So for that reason, I am going to use the trace algebra to shuffle these unitary weights. I can do that. So trace of ABC is equals to trace of B CAB. So this I am referring to is as A, B, and C. So this is C, A, and B. So when I do this, so I end up with this thing. Now this is in this is in right form because I will be just integrating these two terms, and I will end up into the Green's functions. But I cannot do this right away now because I know still the operator h0 and a don't commute, and similarly this and v of tau don't commute. And I still need to decompose this external potential in terms of operator and the field. So this external potential consists of two terms. One is the operator and the other is the field. So this is current is an operator, and this um, uh, vector potential is the field. So that I also need to do. So let's do this. So yeah, so here we are doing this. So B is an operator and C of tau is the field. So we do this, and then we are in a much better situation now. But still, we need to do more algebraic work. So what I do, I replace this variable uh, uh, tau prime that is integrated upon by tau plus t. So once I do this, I um, I can replace this tau prime with t. So I ended up with this simplification, and this external field ends up with tau plus t. Right. And in imaginary time formalism, this is the standard technique that you can move from the time space to the frequency space by integrating over the time. So here you are integrating over the time, and beta is the inverse temperature. So this is 1 by, so beta inverse is kBt. So you have this, so you integrate this, and you move from the time domain into the frequency domain. And similarly, this is in time domain. So we are uh, making Fourier transformation in field from the time domain into the frequency domain. So this is the frequency domain. Okay. Similarly, the frequency domain of the fluctuation in operator A can be done by integrating our time. So here we are integrating our time, and so that's why we have this time integral. So 0 to beta d tau exponential of I omega n tau, and these terms are just present here, like these were present here, or these were present here. So these terms are just present here, and then I have the Fourier transformation of the field. Okay. Now one need to be careful because the integration limit of one integral is the integrand, is the integral variable for the other integral. So in this situation, but there is a very nice uh, um, but we don't need to worry much about it because we know turn on the interaction at tau equals to approaches to infinity, which will make also the limit of tau approaches to infinity. So we don't need to worry about this, and we will set this tau 0 compared to this tau, because if we are considering tau starts from infinity or it goes up to infinity, then we don't need to worry about tau 0. So this goes from 0 to infinity, and now I can gather terms that are dependent on tau, and I can Fourier transform them. So this term and this term depends on tau, and other term I can do anything right now. So these terms depends on tau, and I gather them, and I note 0 to infinity is beta I omega n and I omega n. Basically this should be like 0 to beta and d tau exponential of I omega n minus I omega n of tau is equals to this thing. This is the menu time formalism. Now you come here again and you see that this equation, and from this equation you have exponential of minus I omega n tau, and this is, so this thing has come from that integral, and then you have the Kronecker delta function or I omega n and I omega capital N, I capital omega n. So this will kill I omega n, and this beta will kill this, so you will be ended up with this thing. And there is also this term that is so this thing will become exponential of minus I omega n, because this omega n have become this, so you are ended up with this. Once again you are trying to convert this fluctuation in operator into Green's function, and you can do this because you have one time integration, but these two operators, this set of operators don't commute, like A don't commute with this, B don't commute with this, and they don't commute with each other. So you can do this. Now you need to resolve this issue by applying an identity. That identity is like you have a delta function, delta of t minus t prime, that is equals to this from the menu time formalism, and if you integrate is from 0 to infinity this delta function, it becomes 1. And we also need to use this property of the delta function, that delta of t minus t prime f of t is equals to delta of t minus t prime f of t prime. So you introduce this identity, minus infinity to 0 d of t and 0 to infinity d of t prime, that is this thing, and delta of t minus t prime is beta inverse I omega and t minus t prime, and then you have this, right? Now what you want to do, you want to and you also need to do another thing. So these two variables t and t, they both are having the same notation t and t. Now you want to change it, so you want to change it to one from t to t prime, so that you will integrate one, so that you can utilize these two time where integration variables t and t prime. So what I did, I replaced this t with this t prime, And you see now I can integrate this part and I can integrate this part, and I will be able to write them in terms of the Green's function. So now I collect all of the terms. So I collect t dependent term and t prime dependent term by separating them. So here I have separated them. So I have t prime dependent term here, and here I have t dependent term. So I have this. Now I am integrating t prime dependent term from 0 to infinity. When I integrate this, then I will end up this expression. But remember, there will be another term that will be proportional to infinity times t prime. So t prime will be infinity or I infinity, and there will be I omega n. To avoid this divergence, what you do analytic continuation. You imagine that I omega n goes to omega plus I delta. So if you do this, because of this small I delta, this exponential of I, this become exponential of minus infinity times delta, and this goes to 0. So you only end up with the one term. The same thing happened for with the second term. You get minus infinity to 0, and now you are integrating it. You will be ending up this type of term that will be minus I infinity, and then you will be having I and omega n plus I omega n. But what you do once again this type of substitution. So what it does, uh, in this case this is minus infinity, what it does is it gives you uh, equals to minus infinity and delta, and that goes to 0 as, and that goes to 0. So the second term is no more present in the system. And after this simplification, you can write the fluctuation in operator expectation value due to external interaction in terms of Green's function. So this is the Green's function, and this is the Green's function. And now you can see that these expressions are used a lot in condensed matter physics. Like you use them to find out fluctuations in density, or fluctuation in current, or in viscosity. So this is how you derive the Kubo formula. And this formula can also be generalized to include interaction in the sample. So this H0 does not necessarily have to be a free electron gas. It can also have the interactions. So in that case, your Green's function will be replaced by the full Green's function. But the thing is, this linear response formula will be still valid, and you don't need to worry about this C I omega n, because this is the external potential, and you are probing the system because of the external potential, and you only want to probe it. So you don't want to apply a very strong field that can destroy the sample. So that's why you only want to apply the field that is strong to the limit where the sample is not destroyed. So you only need or interested in the linear response. So this is good that now you have this linear response formula, the Kubo formula, and that can be used to find out these important physical properties. So with this, this is lecture 1, and we will discuss other important properties in the coming lecture. Thanks.